Okay, hi everyone. Let me introduce the speaker today. So today we are very glad to have Joakim here to give the talk. Joakim Blikstad is a fourth-year PhD student at KTH Royal Institute of Technology in Sweden and the Max Planck Institute for Informatics in Germany, advised by Danupon Nanongkai. Previously, he studied at University of Waterloo in Canada. He is primarily interested in combinatorial optimization, including graph matching, maturity intersection, and graph coloring. Today, he will talk about online edge coloring. Let's welcome Joakim. Yeah.
Thank you for the introduction. I'm trying to share my screen here, but it says host disable participant screen sharing.
Yeah. Okay. Can you share your screen now?
Yeah, now it seems to work. Yes. Okay, great. Yes, okay. Can you see my screen? Great. Okay. Yes. Yeah. So thanks for the introduction. Today I will talk about some recent research of me and some of my co-authors on edge coloring, specifically online edge coloring. So this is joint work with between me and Ula and Radu and David. And this talk is based on two papers we had. One was in SOSA this year, and the other one will appear in Stock later this year. Okay, so let's get started. So first off, let's start with the basics. What is edge coloring problem? Just simply given some graph, and you want to color the edges as few colors as possible, and you don't want any two edges which share a vertex to get the same color. So for instance, this coloring is not okay because on this vertex you have two blue edges, right? But this coloring is okay, and it uses 4 colors here of this graph. And but is this optimal, or is there some way we can color this graph with fewer colors? And one easy way to see that it's optimal is to look at the maximum degree. So let's look at this node, for instance. It has degree 4. And throughout this talk, I will use delta to denote the maximum degree. And it's quite easy to see that the number of colors you need is at least delta, right? Because all these colors incident to this max degree vertex must have those edges must have different colors. Okay, but it turns out to be the opposite. This is essentially tight. There's this famous theorem by Weising, which says that any graph can be colored with at most delta plus 1 colors, like any simple graph. In multigraphs, might be a bit more, but we'll focus on simple graphs, right? So how many colors you need to edge color a graph is either delta or delta plus 1. Okay. And there have been a lot of research on edge coloring algorithms in general. First off, there's many algorithms to compute a delta plus 1 edge coloring. One has showed that to actually determine if you can use one fewer color, just delta colors instead of delta plus 1, it turns out to be NP hard. But in bipartite graphs, it's not NP hard, and there are efficient algorithms for it. And there's been a long line of research there as well, trying to get efficient and simple algorithms for bipartite graphs to get the delta colors instead of delta plus 1. And the edge coloring problem, it's also somewhat of a fundamental graph problem. So it has been used as a benchmark in a lot of different settings, where to see how can you translate the graph problem techniques to distributed, parallel, and stuff dynamic. And for this talk, we'll focus on the online setting. Okay, so what is the online setting? So in the online setting, you don't know the graph at the beginning, and it's revealed over time. But we'll assume the max degree delta is known throughout. And once an edge arrives, so let's say this edge arrives, then we have to decide immediately which color to assign it. And this is an irrevocable decision. We cannot change our minds later. So say for this edge, we decide to color it blue, for instance. Then some other edge arrive. We have to decide immediately what color it. Say now we chose red. Now this edge arrives. We cannot use blue or red here because then it's not a valid coloring. So say we use like orange, and so on. So like edge, like the graph is revealed over time. You have to color edges when they come. And there's many different variants on this. For instance, like do you look at edges arriving or like vertices arriving? Do you look at like which order do like things arrive at? Do they come in random order in some kind of like adversarial worst case order? Also, what kind of algorithms do you consider? Do you consider like deterministic algorithms or randomized algorithms? In case of randomized algorithms, you have to talk about what kind of adversary you have. And some people have also studied in some like special graphs, like bipartite graphs. But in this talk, I will mostly focus on like almost the most general variant, which is like edge arrivals. They're like worst case, so like some adversary has chosen like some worst case ordering for your algorithm. And we look at randomized algorithm against oblivious adversaries. If you haven't randomized algorithm against an adaptive adversary in like an online model, it actually turns out to be equivalent to a deterministic algorithm. And determinism in like online algorithms is a bit tricky. So we're not quite there yet. It's like an open problem what to do if deterministic algorithms work or not. Yeah, and we look at completely general graphs. Okay, so this is the setting we consider, and the idea then we want to use as few colors as possible. So how many colors do we actually need? And the question is like, is it still like roughly delta? Like delta was the best like offline algorithm can achieve. Okay, so let's look at a warm up, like a very trivial, simple algorithm. Say the colors are like just numbers, and the greedy algorithm, when an edge arrives, it just picks the lowest number to assign the edge, which is not already blocked for that. So like when some edge E arrives here, you look at all the incident edges to the left and right, like you block these colors, and then you pick the lowest unblocked color. And what we can see here is that a vertex here, how many blocked colors do we have? At most like delta -1, because the max degree is delta. And on the right here, you also have at most delta -1 blocked colors. So in total, it's like 2 delta -1 blocked colors. So this greedy algorithm will be able to find one color among the like 2 delta -1 first colors to like actually assign to E. So this greedy algorithm uses like 2 delta -1 colors. So it's like too competitive, like it's an online too competitive algorithm. It's at most a factor 2 worse than the offline algorithm. Okay. So the big question then is like, can we do better? Can we beat like 2 delta colors? And perhaps surprisingly, and the unfortunate answer is no. But my talk is not over yet. Like there is some like silver lining and some hope to this a bit later. But let's first understand why the answer is no. Like why can we not beat the 2 delta colors? And why is greedy optimal? So there was this paper saying greed is optimal for online edge coloring, more than 30 years old, and they show that you cannot even beat greedy by a single color, like by 2 delta -2 edge colors. The construction is very simple actually. Like the idea is you first create lots of stars where all these nodes have a degree like delta -1, and you create a lot of them, and eventually, if your algorithm just uses 2 delta -2 colors, there's like a finite amount of different stars there could be, like how to assign colors to them, right? Which means eventually by pigeonhole principle, if you create enough of these stars, there must be delta of them which look identical, like they have the same colors assigned to them. And then if you just like add a new vertex here with these black edges, you can see that when you color these black edges, they all need to be different. So you need to use at most delta different colors here, and they can be none of the like colors used in the below ones, because they're all the same there. And below we used delta -1 colors. So to color this, we need 2 delta -1 colors. And this is a lower bound for deterministic algorithms. You can also make it a lower bound for randomized algorithms by, like here, the adversary would have to find, kind of look what those stars is and like see that they're identical, find those delta stars. But for a randomized like for an oblivious adversary, you can just like guess what it is and just repeat it a few times. Right. So you need at least as many colors. So greedy is optimal. So as we saw, the question like greedy is optimal for online edge coloring, but there is a bit of a silver lining. There is a bit of hope, and it's that this like lower bound, it requires a lot of nodes. Like the number of stars for this like pigeonhole principle to kick in is roughly this many, where it's like exponential in delta, because you have like exponential in delta many ways of like coloring like one of these stars, and you need there to be like an overlap, which means that the number of nodes you need here is like exponential in delta, or alternatively, you can think of like the max degree is like roughly log n, or at most log n. This is the only like setting like where the lower bound applies. So this is kind of a low degree graph. And usually when you talk about online edge coloring, you actually talk about it in the regime where like delta is sufficiently large. You also see this in like a lot of other online algorithms. If like delta is like, if you have some parameter smaller than log n, often you cannot really do anything. But as soon as delta becomes larger than log n, you can apply like Chernoff bounds, like concentration inequalities, and get like with high probability bounds and actually beat things. So the new question, can we beat greedy when delta is omega log n? And a spoiler for the rest of your talk is that yes, we can. And in fact, we can use roughly delta colors. So we're like one competitive. And there has been a lot of work on this beforehand. Indeed, this like early paper, which proved the lower bound, said that greedy was optimal. They actually conjecture that when delta, like except for these low degree graphs, like when delta is at least little omega of log n, then you can use roughly delta colors up to some like 1 plus little of 1 term, right? So this is when delta or n grows large, this means like you're one competitive asymptotically. And this is an almost like more than 30 years old conjecture now, and there's been a lot of like partial progress towards it over recent years. So first, people started studying edge coloring in like random order edge arrivals, and there they managed to show that this conjecture holds. So here it's like you have a fixed graph, but the order of the edges arrive, you guarantee that they come in a random order, and then you can like resolve this conjecture. And then people started looking at like vertex arrivals instead of edge arrivals. There they managed to show things for bipartite graphs. They managed to be greedy for general graphs, but just by a bit. And here also, there's one interesting result. Like throughout this talk, I assume like we know what the max degree is, that it's delta. But if you don't know what it is, you cannot, even in like high degree graphs, get down to 1 competitive. And there's actually like a tight result for bipartite graphs, and it turns out to be like this E over E minus 1, which is a constant which shows up a lot in online algorithms, like 1.58 roughly. And then in the most general setting, then there was this very cool paper from a few years ago, which said that you can actually beat greedy in for edge arrivals in like a worst case order, and achieve this like E over E minus 1 competitive ratio. And what I will talk about today is that we can actually, in the most general setting again of adversarial edge arrivals, achieve roughly delta colors, like constant of competitive ratio of 1. And another thing which I think is cute is like this algorithm in itself. I really like it. It's cute. It's kind of simple. I would say it's much simpler than like most of the previous work on this topic, and it works out. It seems like the correct thing to do in some sense. So like, okay. So now after this result, then this conjecture is resolved and becomes a theorem, right? Okay, so that was kind of the overview part. So now I will talk a bit about what kind of techniques we use to achieve this result. And the outline is kind of like this, that in the online setting, it's a bit annoying to think about edge coloring directly. So we convert it to a matching problem instead. I will define the problem of fair matchings. In some sense, an edge coloring is like a covering of the graphs with matchings, right? Like each color corresponds to a matching in the graph. So there's a reduction here showing that these two problems are kind of equivalent. And then we prove like an online fair matching algorithms, and a lot of these previous papers in the field have also gone through this reduction. So we start looking a bit about some natural first steps here, and then look at like what kind of modifications we need. And then the analysis turns out to be quite simple, but rather new to me. Like I had never seen in previous, like I have never really worked with like martingales before, and for me this was like a very acute technique to actually, and powerful technique to prove that these kind of online algorithms work. Okay, so what is this fair matching problem? So you're given a graph, like it will arrive in like an online fashion as like edge by edge, and the goal is to find a matching here. But what do we want about the matching? We want it to be kind of fair, that we pick each edge with roughly the same probability. Ideally, you have like alpha very close to 1, so you want to pick each edge, the matching with probability like 1 over delta. And you cannot really do more, because if there's delta edges next to a vertex, like you cannot pick these edges with probability more than 1 over delta, right? Like you would overflow, right? And so we want like an alpha fair algorithm. It's, say, like in a regular graph, it would be very similar to like a online matching problem where you just want to find a big matching. But in an unregular graph, like if there's like some low degree vertex, you don't really need to match it. Okay, so a first thing we can see, which is quite simple, if we have an edge coloring algorithm using like alpha times delta colors, so like alpha is something like 1 plus epsilon roughly, then we can get like an alpha fair matching algorithm. And the idea is, if you have your coloring, you just pick like a random color in this coloring, and that will correspond to a matching. And since you have this many colorings, like the probability of an edge being in your matching would be like 1 over alpha delta, but like lots of correlations between which edges are in the matching. Right, but it turns out the other direction is also kind of true, that like if you have an algorithm for this fair matching problem, you can actually get like if you have an alpha fair matching algorithm, you can get like an alpha delta edge coloring algorithm with like a small blow up. And this is like, I think almost all recent works in this area, which like beat the greedy algorithm in some kind of adversarial model, use this reduction. And so the new objective now is to find like a fair matching algorithm, which is like roughly 1 competitive, right? Like 1 fair. Okay, so let me quickly talk about this reduction, because it's quite simple. So say we have a fair matching algorithm and we want a coloring algorithm. We just do some pipelining, like we first pipeline the graph G into the fair matching algorithm. It will output some matching M1. And then in the remainder of the graph, we'll pipeline it again. It will output another matching M2, and like these will correspond to our colors. In the end, when like the max degree becomes very small, we'll just fall back to like greedy coloring. So each of these like matchings reduces the maximum degree by roughly 1, because it's like if a vertex had like delta max degree, then it will need to be an expectation almost be guaranteed to be matched. So like you can say, if you run a few of these, you actually have some high probability bounds of the max degree reducing and everything. And for these high probability bounds, you need like delta to be at least like log n. So when delta is like smaller than log n, you just have to do something different. But then we can just fall back to like a greedy and use at most like 200 log n, then like a factor of 2. But this is like a little order of delta term. Right. I won't go too much more into detail of this, but again, this also holds if it's not like 1 competitive, but like a general like alpha fair. And yes, to reiterate, for the rest of the talk, I'll focus on like this fair matching problem and how to find, like try to construct an online fair matching algorithm. Okay, so again, what is the goal? We get the graph and we want to match each edge with probability roughly 1 over delta. To make it a bit more concrete, let's match each edge with probability 1 over delta plus q, where q is some like little order delta term. This will be like the end result, not too important for now, but it's something like delta to the 3 over 4. Okay, so let's see what we can do. There's not so much freedom in the beginning. The first edge arrives. Do we take it or not? Like, if we want to guarantee this statement that the edge is matched with probability 1 over delta plus q, we have to take it with this probability and not take it with this probability, right? So we kind of get this branching. There's no choice for us. Like any kind of fair matching algorithm must do this. Let's see the second edge which arrives. And let's look at this left case first. Here we don't have so much choice. We cannot put it in the matching because then it's not a matching anymore. Here E1 was matched. Right? So here there's no choice. We cannot do anything. We cannot match E2. And in the other side, what do we want to do? Here we want to match E2 with some probability. Which probability should we choose? Is it like 1 over delta plus q? Because we want it to be 1 over delta plus q in the end. This is not quite correct. Like we have to scale it up a bit to like counteract that we could not match E2 on this like left side. So in the end, we want E2 to be matched with probability 1 over delta plus q. But since it can only be matched in like this branch of the algorithm, we have to like scale up with like this probability that we're in this branch. So we'll actually match it with this kind of probability, which turns out to be equal to this probability if you do the calculation. So this is like, so far any fair matching algorithms must follow these steps. Like a bit later, there will be some more flexibility, which we'll talk about, but right now, yeah. So like here, there was nothing to do with probability 1, we just go down here, and here with this probability we go here, with this probability we go here. But this is just a very basic algorithm, like where we have this scaling up factor. And so when an edge arrives, either there's like nothing to do, right? And then we don't do it, but if possible, we want to match it with this probability, and then we scale it up like by kind of this conditional Bayesian approach. But the probability that U and V are actually both free when at this point in time. And if you do this, the probability that E will be in the matching in the end will be exactly what we want. So now you might say like, oh, this is a perfect algorithm, it's nice, but there's one potential problem, like these PTs here, they might not actually be probabilities. You might have accidentally scaled up too much, and then this PT will be bigger than 1. So it's unclear whether this algorithm works or not. So, but let's look at an example where it actually works. It works on a tree. And let's look at the analysis here. On a tree, both U and V are free. That's the probability you want to calculate when like edge ET arrives. And this can be actually split up in probability of U free and probability of V free because they're like independent parts. Like there's no connection here which can create any correlation. This is because it's a tree. And then, so let's focus on probability of U free. Here we look at U, we look at its edges. Each of these edge will, whichever I before, will be matched with this probability by like definition of our pair matching algorithm. So the probability that it's free, and like all these are disjoint events, they cannot, like it cannot match multiple ones. So the probability that will be free will be like 1 minus the current degree divided by d plus b. So like the current degree is 3, so it would be like 1 minus this like target probability times 3 in this case. And the degree is at most delta. If you do this calculation, you see it's at least like q divided by 2 delta or something. So now if we look at PT, we try to bound it. It's like at most 1 over delta plus q. And then we look at the plug in what we got for probability U free and V free, which is like this q over 2 delta term. And we see that this is smaller than 1 as long as we set the q to be like 2 root delta, which is kind of an indication that you need roughly like this slack q to be like root delta. Like you cannot hope for anything better in case, like even if things behave like completely independently and then you're on a tree and things like this. But this is quite nice. And I can mention that like some previous algorithms, for instance, this one I mentioned that this E over E minus 1 algorithm. It kind of uses this idea, you like subsample the graph so that it kind of looks like trees locally. So like all cycles are long. And then you say, okay, it's not quite a tree, but this almost holds. And then they handle the negative correlations. It became a bit complicated in the end, but it works out, and they manage to show this kind of constant. They need to scale down by a bigger constant to show it works, but yeah. But I like this kind of very natural algorithm, and it's open whether it works in general. Like no one knows, there's no counterexamples to it. Maybe we don't just have the right tools to analyze why this potential problem never happens in a journal graph. Okay, but I will suggest an alternative algorithm, which I think is like equally natural, where we actually can like solve this potential problem and have tools to analyze that it's at most one. And here we will say that the scaling factor here and like the probability in U and V are free, it will depend on like previous choices we take. It's like in the current execution path of the algorithm. I'll explain this more soon. Okay, so to try to formalize it a bit, this is the algorithm from our paper where we see that, again, the probability we want to match an edge is like 1 over delta plus Q. And it's divided by the scaling factor of like all the neighboring edges will have some probability of being matched. And then we just scale it up by it. But here we just use the scaling factors. Like these are edges which arrived earlier in the algorithm. So these themselves have had assigned like this P of ET value. So these values depend on the run of the algorithm and whether things got matched or not. Like maybe some of them are set to 0 because they were like something out here got matched or not. So these values depend on the run of the algorithm. And then we use those current values actually used in the execution path of the algorithm in our scale up factor. I will make an example here soon to make it more clear. But another alternative way to view this algorithm is that what I mean here when saying scale up with probability UV both free in the current execution is actually, if we look at the event R to be like all the randomness we used in our algorithm, like outside of this picture here. So like if there were some edges further away, like not in the immediate neighborhood of this edge, like everything outside, if we condition on all the random bits we use to decide whether those edges are matched or not, what we actually compute here is the probability that U and both U and V are free, like conditioned on all the randomness like outside, except for, so the only randomness in this expression are the randomness we used on like these edges here and these edges here. Okay, what we actually do in our paper, we have to define like a slightly more complicated algorithm. It's not so important, but to keep some invariance and not make things explode, if some p-value becomes too large, we kind of set it to 0 instead. It's not super important. Like this algorithm will work. It will need like some extra log n factor because here you need like high probability in n. A more fine-grained algorithm can get like, you only need high probability in delta, which might be much smaller. Okay. Either way, but let's look at an example to understand what this new scaling thing actually means. So we already had this example from earlier, and here we said, so far there was no choice whatsoever. Like any fair matching algorithm must exactly use these kind of probabilities, right? But let's see now when a third edge arrives. Let's see E3. Now, like here, there's like in the middle one, there's no choice because E2 is already matched. We cannot do anything. But here we have 2 places where E3 can be matched. And a good question is like, should we use the same scaling probability there or different scaling probabilities? So this like first original algorithm I talked about would just calculate the probability of U and V being free at this step, which would look at like all these leaf nodes in this kind of tree. It's not even clear how to do it computationally efficient. In online algorithms, we don't care about it too much, but so that's somewhat of a minor issue, and then see that the probability that both U and are not free is exactly this probability, and it would use the same scaling factor no matter if we're over here or over here. But this new alternative algorithm I'm suggesting here, where we kind of condition on things happening outside of the immediate one neighborhood, would actually use different probabilities here. It would kind of say that what happened for this edge E1, like we want to condition on this kind of randomness. So here in the left branch, like E2 was taken with probability 0. So there's no need to scale up E3 at all. So the scaling factor, like here, if you condition on the edge E1 being matched here, like the probability of both these vertices being free is exactly 1, right? On the other hand, on this branch, you condition on E1 not being free, and here you get like a slightly higher scaling factors. So if you compare them, here we used this kind of scaling factor for both. Now in the new algorithm, we use like different scaling factors. One is like larger, one is smaller. Okay, and this has the advantage that it makes it much easier to analyze. However, now it's not even clear that it works in a tree anymore, because the same analysis as before will not work in a tree. Like we see already here on a tree, these two algorithms will behave differently. And actually with some low probability, the new algorithm will fail on a tree. Okay, but what do we actually need to prove? Again, if you do these things, since you, by law of total probability, this conditioning, and you sum things up, you still get the right marginal probability. So the probability at the end that you match an edge will be exactly what we want. It's like 1 over delta plus Q, like the target. So again, the core of the analysis is to prove it's actually a well-defined algorithm, that these PETs are less than 1. And in particular, we can focus on the scaling factor. And we want to show that this scaling factor is not like, I guess, we don't scale up too much, right? In fact, instead of proving it's smaller than 1, we'll prove it's like much smaller, like roughly 1 over root delta. Originally, it's like 1 over delta, so you can expect it to not climb more than like 1 over root delta. And why we need this is because if things gets too close to 1, like the algorithm breaks and like errors propagate too much. But as long as everything stays under this value, we can prove that everything still stays under this value. So we need to like a stronger induction hypothesis kind of. And to compare a bit with previous work here, previous work kind of tried to control the correlations, like between different edges, whether they get matched or not, and try to say like, oh, we have almost negative correlation and stuff like here. In our approach and how we analyze it, we will embrace the correlations. We don't care about the correlations, like our analysis will work no matter the correlations. And this allows for like a kind of cleaner algorithm in the end. Like this algorithm is quite simple. Okay, so let's give some more details for the reduction. Sorry, for this analysis. So let's say these are edges which will appear in the future. They have not appeared yet. And so at this point in time, like our estimate for what the probability that will take an edge here will be like 1 over delta plus Q, because no edges have appeared yet. Like it's edges in the future, we don't know about them yet, but for the purpose of the analysis, let's pretend we know what it will be, like in retrospect. And then we kind of look at this scaling factor, which the scaling factor here can be split up kind of on the scaling factor on the left here and scaling factor on the right. So let's focus on the scaling factor on the left, like incident to this U here. The scaling factor here would kind of be the probability of U being free. In the future, so like right now, U is free because no edges has arrived, but then we want to say the probability of U being free when ET arrives, given that like these are the kind of probabilities which these edges will be taken with, which have not arrived yet. So you can kind of imagine writing like some number on each edge, and these numbers will be like updated throughout the algorithm. So what happens here is that like the probability of U being free, these are independent events. It will be like 1 minus the sum of the PETs here. Note down here we have a product, but it's kind of because when say like this edge arrives, these ones will be scaled up a bit, but here we ignore like the effect of like scale, like if this one is not taking into like scaling up these to just get the sum. It's like essentially equivalent. So let's look at what happens when some edge over here arrives, like some edge f here. It will have some probability f of being taken. It's not super important what this probability is, because we look at the cases here. If f is matched, then this p2, like this p of e2 value will become 0. Like there's, again, these dotted edges have not arrived yet, but we can still talk about it in the analysis. If this edge f is matched, there's no chance for this et2 edge being matched, so its probability is updated to 0. On the other hand, if f is not matched, what this algorithm will do is just update what this value is. So it will now be a bit larger than 1 over delta plus q. But these two things happen with respect to probability, like p of f and 1 minus p of f. So in expectation, this value here stays the same. So in expectation, like the value of SU, if you see it as like something developing over time, stays the same, right? So like our estimate for in the future, after everything has arrived, just before ET arrives, that it will be free. Like we keep track of kind of an estimate along what this future probability will be throughout the algorithm. Okay. And again, the goal here is to show something that this SU, which will take part in the scaling thing, is not too small, because if it was too small, this probability would be like too large. Okay, so here is kind of nice. So if you look at this SU happening over time, like in the beginning, it's set to some value, and then when some edges like this edge F arrives here, which is like 2 hop away, it will update some values. They will go to like maybe this SU will increase a bit or decrease a bit. So you can see it as a random walk, like either it increases, maybe next edge arrives, it decreases. In total, you will have like delta squared steps. Like you have delta edges here, and then delta edges incident here for each of these vertices, like for each of these edges, right? So you can model this as kind of a random walk. And you know that initially, all the estimates was like 1 over delta plus q. If you do the calculation again, what this should be, you get, it's roughly like q over delta. In the end, you want to show it at the end, it's kind of high. So you have this kind of random walk going up and down. You know it begins at q over delta. You know in expectation, it stays on the same level in each step it takes. And so what we want to show is that it never falls too far below this expectation. So we want to show some like concentration properties. So usually what takes part here is that like to show concentration properties, we have to look at the number of steps we take and like the size of the steps and some kind of variance of the steps and things like this. And since we assume that these values, like all the p-values were not only smaller than 1, but like much smaller than 1, like roughly 1 over root delta, these steps are not too large. Like when something is set to 0, we don't lose like go 1 in the step, we go like 1 over root delta in the step. And same here, like the scaling factor is not too, like it's very close to 1. So the steps are kind of small. So how do you analyze such a process? If you have no correlations whatsoever, you can just assume things are independent. Like each step here is kind of independent. There's no correlations between the edges. You can just use Chernoff bounds. And you would get the same result as we get in the end. You would get like Q is roughly equal to delta to the 3 over 4 for this to work, for never to fall below. But now we do have correlations. So then there's this very cool technique of martingales, which comes into play. And like a process like this random walk is a martingale if like in expectation, each step you take is 0, like conditioned on no matter what happened previously, basically. And our scaling factors here will actually be a martingale, like we showed in the last slide that this expectation is 0, kind of be implicitly conditioned on like what happened before. And then, as I said, so now there's some hope to show, like use concentration inequalities for these martingales, which are more powerful than Chernoff bounds because they can handle some kind of implicit correlation. So the first concentration inequality to go to, if you know things about martingales, is probably like Atsuma's inequality or something, but it's not too strong enough for us here because we have like too many steps, and like most steps are like this and they're very small, but these steps are a bit bigger, but there's like only delta of these bigger steps up here, while there can be like delta squared small steps. So we need like a more fine-grained concentration inequality, which can handle like these kind of differences in step sizes. And this is what Friedman's inequality does. It says that if you have a martingale and the step size is bounded by some A, and this observed variance is kind of saying what like the average step size is instead. Like here it counts the, like throughout your execution, what was the variance of all the steps you took. And if some of them, like if you have delta squared small steps and delta big steps, it's still fine. And then it says, Friedman's inequality says that the total amount you walk, like either up or down, the probability that it's like you deviated more than epsilon is something like this, depending on the observed variance and the step size. It looks similar to Chernoff bound, just a standard concentration inequality, but a quite powerful one. And I will not bore you with the details on like bounding the step size and the variance here. It becomes a bit technical in the end, but if you set it up correctly, it just works out. It's just some calculations. Okay, and that's basically the whole analysis of our algorithm. And yeah, it's not super complicated. The paper turns out to be pretty short, but the main idea here is this like really cool thing to kind of model it as this like martingale process. Like you have these values P, which like change over time, things like this. So this concludes kind of the main technical result, where we managed to show that there is some like online algorithm which outputs a matching M, where each edge is matched with probability at least 1 over delta plus Q, where Q is something like this for the concentration inequalities to work out. In particular, this is like little order of delta. Okay, so that's kind of the technical part of the talk. So to summarize, what we saw was that first we saw that for low degree graphs, greedy is optimal. We cannot be 2 delta, but otherwise in like higher degree graphs, we have this fair matching algorithm, and as a corollary, with this aforementioned reduction, like pipelining several calls to this fair matching algorithm, we managed to show that we get like roughly delta colors, like 1 competitive when delta is large enough. And this reduction requires like delta is at least log n. Yeah. And I want to quickly mention some like extensions and generalizations, which I think kind of shows that we have found like the right way to do it. It's like easily extendable to some other settings. One of them is like list edge coloring, where instead each color has like a separate input list. So you're given these lists in an online setting. When an edge arrives, you're given like which colors are possible to color this list. And as long as these lists are large enough, like a bit larger than delta again, we can pick a listed coloring. There's also the notion of local edge coloring, which means that normally the number of like which colors you're allowed to use depends on like the global maximum degree. Here it's kind of for an edge UV, you look at the local maximum degree and say that like say the colors are from like 1 to like 1, 2, 3, 4, and so on. So here it kind of in a sparse part of the like in a part of the graph where the low degree is low, you actually kind of get the coloring as if like the max degree was much smaller there. And of course we need this like additive log n term here because it's impossible if like the max degree is like constant to get anything better than log n. Right. So another very cool generalization, I think, is of this like technical result of like the fair matching algorithm. And And that's that we can do like an online rounding of like a fractional matching as long as the input fractional matching is kind of spread out. So say we're given a graph in an online setting, so edges arrive, and along the edges also arrives like some values xe, which is like a fractional matching. And let's assume it's spread out. So like xe's are quite small, like they're smaller than some epsilon, and I feel like epsilon to the 5. Then we manage to almost losslessly round this, like we have some like 1 minus epsilon loss. So we pick edges e in a matching. So we with probability xe. And then the online setting. And first, when I realized we could do this, I was a bit surprised because like it also works in general graphs. Like we never assume the graph is bipartite. So here we like round a fractional matching to an integral one. And in the non-bipartite graphs, there's this like integrality graph of 1.5. So is something wrong here? No, it actually turns out the integrality gap is like, if you assume the matching is spread out, like you add constraints like this, then the integrality gap becomes like 1 minus epsilon instead. But it also shows that our algorithm is essentially tight. Like we cannot have like a lossless rounding if it works in general graphs. Okay. And to see that this kind of algorithm here is a straight generalization of like our fair matching algorithm is to just input like the static matching where like you assign a fractional value of like 1 over delta on each edge, then you match each edge with probability roughly 1 over delta. And it's like a very spread out matching as well. Right. Okay, so let's look at some open problems. I think one of the cooler open problems here is if you can achieve deterministic algorithms. Or equivalently, it's like an randomized algorithm which works against an adaptive adversary. They turn out to be equivalent in the online setting because you don't care about like the computational efficiency of that. And here it's kind of completely open whether you can be greedy even in other settings like vertex arrivals and things like this. And I'm starting to believe it's possible. Like at first I thought it was some lower bound, but I think it should be possible. Okay, some other maybe more easily like low-hanging fruit is to try to correct the asymptotics. Like the lower bound says that like you need at least log n colors, kind of from this like lower bound we showed today. There's also another lower bound saying you need at least like root delta colors. This is the number of colors we use in our final algorithm. This term is kind of from the fair matching algorithm. This is from like the reduction to fair matching. So like there's still some gap here. And it would be nice to get the dependence on delta down to like root delta or something. Another thing is that actually for randomized algorithms, the lower bound actually only applies when delta is at most root log n. So between like delta, between root log n and log n, it's unclear whether you can beat greedy or not. Like it seems kind of difficult because you need some kind of concentration inequalities. And for these, you usually need like log n concentration. But on the other hand, it's very unclear on how to improve the lower bound. I actually have started thinking about this a bit with some of my courses, and we start to believe the answer might be different, like for edge arrivals and vertex arrivals. Like we think for vertex arrivals, you might be able to beat it. For edge arrivals, you will not. Okay. Another generalization is multigraphs, right? In the offline setting, you know, you need at most like like 1.5 delta, or like delta plus mu, where mu is the multiplicity, like the number of parallel edges colors. And can we get something close to like either of these two values for multigraphs, or even hypergraphs, like coloring hypergraphs? And my feeling is that the tools should generalize somehow. Yes. And I think that wraps it up. Thank you.
Thanks. Yeah, it's a very nice talk. It's very clear. Yeah. Let me first stop the recording and ask some questions.